Hi everyone, welcome to our walkthrough for CSM 16B, Spring 2021, worksheet number 4. I'm Anthony. So this week we're really going to be focusing on Bodhi plots with a slight introduction to systems. So Bodhi plots is a mechanism we use to actually figure out the tendency of the transfer function h of j omega as the frequency omega changes. Okay, so the Bodhi plots consists of two plots: a magnitude plot where you actually plot out the magnitude with respect to the, the frequency omega. We also have a phase plot where you just plot the phase of the transfer function as omega changes. Okay. So to actually see the tendencies, we usually use a log scale on the omega. If we decided that we want to use a log scale on a magnitude, this is what we call a log scale. Okay. In the case of a phase, it really doesn't make sense if we draw the phase in terms of its logs. So we just do a semi-log scale. Just draw out the phase on the y coordinates, and we call that a semi-log scale. In reality, the magnitude plot, it can also be on a semi-log scale. But the phase plot, it really doesn't make sense to draw out the phase plot in a log scale. Okay. So to actually see how we draw out these Bodhi plots, let's actually take a look at a couple of examples. As always, if you want to take some time to look at the question yourself, try them out yourself, you can pause the video for a couple of minutes. And 3, 2, 1, unpause. For this very first question on the worksheet, we have Bodhi plots for filters. So first off, we want to consider the following transfer function of a low-pass filter corresponding to the diagram on the left. Okay, so we have h of omega being equal to 1 over j omega c1 r1 plus 1, where R1 is equal to 100 ohms and C1 is equal to 100 picofarads. And the first thing we're asked to do is to find its cutoff frequency. Well, if you recall from worksheet 3, we know that the cutoff frequency of either a low-pass filter implemented using RC, an RC circuit, or a CR high-pass filter, both of their cutoff frequency is 1 over RC. Okay, so we know that the cutoff frequency is omega C, which is equal to 1 over RC, which is equal to 1 over 10 to the 2 times 10 to the negative 10, because 1 picofarad is equal to 10 to the negative 12 farads, which is then equal to 10 to the 8 radians per second. Okay. For those of you guys who didn't quite watch the walkthrough for worksheet 3, or if you simply forgot why we have this cutoff frequency, recall that the cutoff frequency is defined as the frequency at which the magnitude of the transfer function is 1 over root 2. So since we know that we're just going to write out the magnitude of the transfer function. Since we know that the magnitude of the quotient in terms of complex numbers, the magnitude of a quotient is just the quotient of the magnitude. Okay, so that's actually equal to 1. The magnitude of 1 is just 1 over the magnitude of j omega r1 c1 plus 1. Okay. So that is actually equal, because j is just the imaginary unit, so that is actually equal to 1 over root omega r1 c1 squared plus 1. Okay, so we want this value to be 1 over root 2. Then essentially we're trying to find an omega such that omega r1 c1 is equal to 1. Okay, and so omega, the cutoff frequency omega c, is just 1 over rc. As a reminder, the cutoff frequency of filter doesn't have to be 1 over RC. It's just it just happens that in the case of a CR filter or RC filter, we have this cutoff frequency 1 over RC. It doesn't have to be always like that. So in the second part of the question, we're asked to sketch its phase and magnitude. So we're asked to actually draw the Bode plots. So to actually draw the Bode plots, we're using the straight line approximations. We're dividing the graph into half, just doing a casework. Either your omega is less than omega c, or your omega is greater than omega c. When omega is less than omega c, we assume, though that this is just an assumption, this is not always true, assume that omega is way less than omega c, and it's negligible as compared to omega c. And for the case where we have omega greater than omega c, we also assume that omega is way larger than omega c. That omega c, although it's a constant, it's sort of a constant. When you have omega c over omega, it just tends to 0 in that case. And do those kinds of straight line approximations. Okay, so that's how we actually draw the Bode plots. We just divide the graph into half and do a casework. This is just the general methodology we use to actually draw the Bode plots. So to sketch out its magnitude, to do the magnitude plot, I should probably write it down here. We have h of omega being equal to 1 over j omega r1c1 plus 1. So we know that omega c is equal to r1c1, 1 over r1c1. And so this is actually equal to 1 over j times omega over omega c plus 1. Okay? Just for the sake of simplicity, just write it out that way. And as I explained earlier, we are going to be dividing the graph into 2 parts. The first part, we have omega less than omega c. So our omega c is 10 to the 8th. Right, so we're just going to put 10 to the 8th in the middle of the graph. This is our omega, and the y-axis is going to be used for the magnitude of h of omega, of the transfer function. Okay, so this is kind of ugly. I'm just going to erase this. Move it down here. Okay. So as I said, since we want to divide the graph into 2 parts, we're just going to put the cutoff frequency 10 to the 8th in the middle of the diagram. And for the sake of Bode plots right here, we're just going to use the log scale. So on the x-axis, just put in the corresponding exponentials. And on the y-axis, we don't know what's going to happen yet. Okay, we don't know what the magnitude is going to look like, so we're just going to keep it like this for now. We know that the magnitude of the transfer function, as we derived from part 1, is equal to 1 over root omega r1c1 squared plus 1, which is then equal to 1 over omega c squared plus 1. Okay, so as I explained, we do a casework on the value of omega. If omega is less than omega c, we assume that omega is way less than omega c. This is how we do the straight line approximation. So if omega is way less than omega c, then this term on right here, it just tends to 0, right? So omega over omega c, it tends to 0. And so the transfer function does its magnitude, the magnitude of h of omega, it just tends to 1. Okay, so it's approximately 1. Okay. So for the part where omega is less than omega c, we just say that h of omega is close to 1, is approximately 1. Since we're doing a log scale, we're gonna be putting 10 to the 0 on the very top. Put it down in that order. 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, 10 to the negative 4, 10 to the negative 5th. Okay, so when the omega is way less than omega c, when omega is less than omega c, we just say that the magnitude it's close to zero. It's close to 1, which is 10 to the 0. So we draw this line. Okay. Similarly, when omega is way larger than omega c, we know that this omega over omega c is a very large value. We're not going to say it tends to infinity, because then we wouldn't be able to see the tendency of things. But rather, we're just going to ignore, it's going to be way larger than the one term. So we're just going to ignore this one term and say that h of omega, its magnitude, is approximately 1 over omega c, which is equal to omega c over omega. Okay. So as the frequency gets multiplied by 10, we know that the transfer function's magnitude gets multiplied by 1 over 10. And so that means we're going to have a linear graph on this graph, okay, on the magnitude plot, like this. Okay, so that pretty much concludes our magnitude plot for this very transfer function. Here we are assuming that omega is greater than omega c, and so we're assuming that omega is way larger than omega c for the sake of convenience. Now we try to draw its phase plot. So to actually draw the phase plot, we use the same technique that we used when drawing out the magnitude plot. That is, we divide the graph into two parts. Okay. We do a casework on the omega, the frequency. We analyze how the angle, how the phase of the transfer function is going to change when omega is less than omega c and when omega is greater than omega c. Okay. So when omega, I should write it down, the angle of h of omega, the phase of the transfer function, is equal to negative the phase of j omega r1 c1 plus 1. The reason behind that is that the angle of a quotient is equal to the difference between their corresponding angles, phases. Okay. As I explained, if we write both of these in their polar forms, that is, if we write a being equal to r1, a equals r1 e to the j theta 1, and b equals r2 e to the j theta 2, then a over b is equal to r1 over r2, assuming r2 is not equal to 0, times e to the j theta 1 minus theta 2. And so the phase of a over b would then just be theta 1 minus theta 2. Okay, so that's some sort of mathematical fact we want you to know about phasors. So since r1 c1 is just 1 over omega c, we just write it as negative the phase of j times omega over omega c plus 1. Okay, so when omega is way less than omega c, we should actually draw out the coordinates for that. We have the real part, we have the imaginary part. When omega is way less than omega c, this is actually close to 0, right? This actually is close to 0. So this phase of h of omega, it just tends to the negative angle of 1. Since 1 is a real number, we actually draw out its coordinates, which is 1, 0. And the coordinates, which implies that its angle would then just be 0. And so the phase of h omega would just be 0. Okay, so when omega is way larger than omega c, that's sort of an assumption that we make when we are drawing the Bode plots. We still try to find its coordinates within the coordinate system. We see that omega over omega c is imaginary part, it's going to be very large. So it's going to look something like this. Okay. As omega goes to infinity, it's going to tend infinitely to j times omega over omega c, whose phase we know is pi over 2. So the angle, the phase of h of omega, it just tends to negative pi over 2. So as we explained, as omega tends to infinity, the complex number j times omega over omega c plus 1, it just tends to j times omega over omega c. Okay, so that is entirely on the imaginary axis. And its phase will be pi over 2. Since we have a negative sign in front, our corresponding phase of the transfer function will then just tend to negative pi over 2. Okay, so to actually draw out this phase plot, you just put 10 to the 8th in the very middle. The omega. This is the phase, h of omega. When omega is way less than omega c, we know that the angle will then just be 0. Okay, so we're just going to draw something like this. And when omega is way larger than omega c, we know that the phase is going to tend to negative pi over 2. So we're just going to say this is negative pi over 2. Okay, and so we're going to draw something like this. Okay. Since we know that the angle is not going to jump over time, to do our straight line approximation, we just connect those two parts together. Okay. And so this is our final phase plot. All right, so that pretty much concludes our walkthrough for the first part of this question where we considered a low-pass filter. And now off to part B, we now consider the transfer function of a high-pass filter. The transfer function is then h of omega being equal to j omega c to r2 over j omega c to r2 plus 1, where r2 is 1 kilo ohm and c1 is actually c2 is equal to 10 nanofarads. So we know that this is actually equal to 10 to the 10 times 10 to the negative 9 farads, which is 10 to the negative 8 farads. So in the first part, we're asked to find its cutoff frequencies as well. So if you remember from last section, the cutoff frequency of a high-pass filter is exactly the same if omega c being equal to 1 over R2C2, which is equal to 1 over 10 to the third, which is R2, times 10 to the negative 8th, which is C2. This is equal to 10 to the 5th radians per second. If you sort of need a refreshment on how we actually derive this cutoff frequency for a high-pass CR circuit, we can actually write out the magnitude of this transfer function. Since the magnitude of a quotient is just a quotient of the magnitudes, we see that this is equal to the magnitude of j omega R2C2 over the magnitude of j omega R2C2 plus 1. And then we compute the magnitudes on each side separately. So this is actually equal to omega R2C2 over root omega R2C2 squared plus 1. Okay, for the sake of simplicity, we just divide both sides by omega R2C2 to get this being equal to 1 over root 1 plus 1 over omega R2C2 squared. So so if we want this value to be 1 over root 2, we are essentially asking that omega c be a value such that 1 over omega R2C2 is equal to 1. Right? And so omega is equal to 1 over R2C2. And we plug in the values just like what we did before. Okay. We should note that this isn't always true when it comes to filters and cutoff frequencies. It's just because we are doing CR and RC circuits, and they happen to have the same cutoff frequency, the same formula for cutoff frequencies, 1 over RC. It's just a coincidence. I should make that extra clear. And then after part two, we want to sketch its phase and magnitude. Okay. So again, we want to divide it into two parts. So we put the cutoff frequency 10 to the 5 radians per second in the very middle. Just the x-axis is used for the frequency, and the y-axis is used for the this is the magnitude plot, is used for the magnitude. Okay. Again, we put this cutoff frequency in the very middle of the graph and do a casework based on the omega, based on its relationship with omega c. So if omega is less than omega c, we put it on the left-hand side, whereas if the omega is larger than omega c, we would put it on the right-hand side. Okay. And then we fill in the corresponding frequencies because we're on a log scale, so that's going to look something like this. Okay. And we know that the magnitude of the transfer function is equal to 1 over root 1 plus 1 over omega r2c2 squared. Since 1 over r2c2 is what we define as omega c, we know this is equal to 1 over 1 plus omega c over omega squared. Okay, so when omega is way less than omega c, when omega is way less than omega c, this term is much more dominant than this term, right? So we can just take out the one term and see that h of omega, its magnitude, is approximately 1 over omega c over omega, which is omega over omega c. Okay, as we explained earlier, since as omega gets multiplied by 10, we see that the magnitude of the transfer function gets multiplied by 10. And so since we're on a log scale, we know that this is going to approximate to a straight line. Okay. On the other hand, if omega is way larger than omega c, then the transfer function, its magnitude, we know this is going to tend to 0. This term is going to tend to 0. And so this is going to be approximately just 1. Okay. So we're just going to draw out the magnitude plot. When omega is larger than omega c, we assume that omega is way larger than omega c, and we do this straight line approximation. Okay. So we get this straight line over here, right on 1, since 1 is equal to 10 to the 0th. And when omega is less than omega c, we assume that omega is way less than omega c, and something. And as we derived, the transfer function's magnitude is approximately omega over omega c. Okay, it says if we multiply omega by 10, the magnitude gets multiplied by 10. So this is a straight line. Okay, this is just a straight line since we're on a log scale. Okay, so it's going to look something like this. Okay, and so we have our magnitude plot. Okay, now let's actually try to draw out the phase plot together. So draw out the phase plot. To actually draw out the phase plot, we first try to rewrite h of omega so that it looks nicer. We know that h of omega is equal to j omega r2c2 over 1 plus j omega r2c2. So we're just going to divide both sides by j omega r2c2 to get something like 1 over 1 minus j, because 1 over j is just negative j, times 1 over omega r2c2. So since omega c is equal to 1 over r2c2, we see that this is actually equal to 1 over 1 minus j times omega c over omega. Okay? And since the phase of a quotient is just a difference in the actual phases, we see that the phase of h of omega, the phase of h of omega, the phase of the transfer function is equal to negative phase of 1 minus j times omega c over omega. As omega is less than omega c, we just assume that omega is way less than omega c. And we just draw out our complex coordinates, just like a two plane, with the real axis and the imaginary axis. We know that the real part of this complex number is just going to be constantly 1, right? So it's going to be a constant. So this is 1. And the imaginary part is going to be negative omega c over omega. Since omega c and omega, they're both positive, it's just going to tend to negative infinity. Okay, so as it tends to negative infinity, this complex number is just going to be closer and closer and closer. They have the same real part, just the imaginary part just keeps getting smaller. It's just going to tend to a part of the imaginary axis whose phase is just going to be this angle, which is negative pi over 2. So the phase of h of omega is just going to be approximately negative pi over 2, which is pi over 2. And when omega is greater than omega c, we just sort of assume that omega is way larger than omega c. In that case, the imaginary part, negative omega c over omega, it just tends to 0. Okay, it just tends to 0. And so the phase of h of omega just approximately negative the phase of 1. Okay, so this 1 is just on the real axis. We know that its phase is actually 0. So it's going to be negative 0, and so it's 0. Now we draw out the phase plot. As always, we divide the graph into 2 based on where our cutoff frequency is. And we want to put our cutoff frequency in the middle. So this is the frequency, omega. Our cutoff frequency is 10 to the 5th radians per second. When omega is less than omega c, our approximation says that the phase is just going to be pi over 2, right? It's just going to be pi over 2. Just going to be pi over 2. When omega is way larger than omega c, we say that the phase is approximately 0. Okay, we say that the phase is approximately 0. And so this is actually, just draw something like this. Okay, and since this is just a continuous function, we want it to look continuous rather than having a huge jump in the middle. Just making it look a little bit nicer. Okay, and so this is our final phase plot for part B. Okay, in part C, we're asked what happens if we cascade the two filters together with a unity gain buffer in between them. So this is what we call a bandpass filter. So it's gonna look something like this. So first off, you have the slow pass filter, which is an RC circuit. You pass it through a unity gain buffer. This is a positive non-inverting input. And then you have the inverted input connected directly to the output. That's a negative feedback loop. So this is just a buffer. And then after that, you have this high pass filter. And this is your final V out. So this is going to be your final V out. These are all grounded. And this is just your final V out. Okay. The resulting transfer function is going to be just the product of the two transfer functions, because by the golden rules of the op amps, there's not going to be any current flowing to and from either of the filters. So we can just treat those independently because the KCL and KVL equations are not going to change. If you actually think about it, the equations is not going to change, and they just operate independently because we can just treat the output of the first filter as the input to the second filter. Okay, so in that case, we just multiply things together. So the resulting transfer function is just going to be h of omega being equal to 1 over j omega c1 r1 plus 1 times j omega c2 r2 over j omega c2 r2 plus 1. Okay, so what are its cutoff frequencies? In this diagram, we first have a low pass filter, and then we have a high pass filter. Okay, so the low pass filter, it just blocks out the higher frequencies, and a high pass filter just blocks out the lower frequencies. I think in terms of this question, it's not like trying to rigorously ask you to find such an omega such that the magnitude of the transfer function takes on the value of 1 over root 2. But rather, I think we're trying to intuitively understand how this bandpass filter behaves in certain conditions. We know in the case of a low-pass filter, if you go beyond omega c, so if you go beyond omega c of the low-pass filter, then the signal gets blocked, right? It blocks all signals with omega being greater than omega c. Whereas in the case of a high-pass filter, it blocks all signals with omega less than the omega c, the cutoff frequency of the high-pass filter. So the general behavior of this bandpass filter is that whatever is in between those is just going to pass through, right? But if you have something that's out of this range, it's going to be either blocked by the low-pass filter or it's going to be blocked by the high-pass filter. Okay, so the cutoff frequencies in this case, it's just going to be the cutoff frequencies of the two individual filters. Okay, so the lower the cutoff frequency given by the low-pass filter would just be 1 over R1C1, which is 10 to the 8th radians per second. Whereas the cutoff frequency given by the high-pass filter is just 1 over R2C2, which is 10 to the 5th radians per second. Okay, so we notice that a low-pass filter has a higher cutoff frequency than a high-pass filter in order to actually build a bandpass filter, because otherwise, all signals, it just gets blocked by either the low-pass or the high-pass filter, and nothing can pass through. And it doesn't really make any sense to build such a filter that blocks every single signal. All right, so now we sketch its phase and magnitude. Instead of actually doing everything from scratch, there's a hint that says, how can we actually combine the plots of the individual filters together? I think here we should note that we're on a log-log scale. For the magnitude plot, and we're on a semi-log scale for the phase plot. Okay. So since h of omega is equal to the transfer function of the low-pass filter times the transfer function of the high-pass filter, we know that its magnitude, as we pointed out before, the magnitude of the product in complex numbers is just the product of the magnitudes. Just going to be the magnitude of the low-pass transfer function times the magnitude of the high-pass transfer function. Okay. And since we're on a log-log scale, we see that the log of h, the log of the magnitude of h of omega is just equal to the log of the magnitude of HL omega plus the log of HH omega, its magnitude. Okay, so basically we're just adding together the two plots since we're on a log-log scale. Okay, so this is 10 to the 0, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3rd, 10 to the negative 4th, 10 to the negative 5th. And we want to put our cutoff frequencies 10 to the 5th and 10 to the 8th in the middle of the graph. Okay. This time around, we have two cutoff frequencies. So this is for the high pass, this is for the high pass filter, and this is for the low pass filter. This is for the low pass filter. So for the low pass filter, we know that it lets all signals with a low frequency pass through. So for the low pass filter, the magnitude plot is going to look like this. Right, this is for the low pass filter. Okay. And then for the high pass filter, it's going to let all signals with a higher frequency pass through. So it's going to look something like this. As we try to add together these two plots, be aware that 0 is at the very top, which might be a little bit confusing. If we try to add together these two plots, we're going to get something like this, which is sort of the expected behavior of the bandpass filter. So all signals with frequency between the two cutoff frequencies, it just passes through, whereas all signals outside of that range just doesn't quite pass through. Okay. And then for the phase plot, we use the same tactic. We say that h of omega is equal to HL of omega times HH of omega. And since the phase of the product is just the sum of the phase, we know that the phase of H of omega is equal to the phase of HL of omega plus the phase of HH of omega. Okay? So we can just simply find the phase plots for both of these, for both filters, and then just add them together, since we're just on a semi-log scale. So we're just trying to do the same thing as in the magnitude plot. We want to find the cutoff frequencies. In fact, we want to put the cutoff frequencies in the very middle. They're sort of ugly. I want to put the cutoff frequencies in the middle. Okay. And we actually look up to parts A and part B to see that, so actually say this is pi over 2. This is actually like negative pi over 2, let's say. Then we're just going to say this is pi over 6, and this is negative pi over 6. So first, we actually try to draw out the phase plot for a low-pass filter. Just going to be using the same colors. So we know that the low-pass filter is a value of 0 all the way to its cutoff frequency, and then it drops to negative pi over 2, right? So it drops to negative pi over 2. And then for the high-pass filter, it just starts out at pi over 2, and then drops to 0 at its cutoff frequency. So it's going to look something like this. As we add together the two plots, we're just going to get a final plot that looks like this. Since the line in the middle, straight line in the middle, it just represents the angle 0, the phase 0. Okay, so as we add them together, it's going to look like this. All right, and that pretty much concludes our walkthrough for question 1 on this worksheet. You should be extremely aware that although straight line approximation is not too complicated to do, it doesn't accurately represent how the Bode plots are actually going to look like. It doesn't like 100% accurately represent how it's going to look like. As an example, if you look up to part B, in terms of the magnitude plot, even in a log scale, it's going to look something like this, instead of what you're actually seeing in straight line approximations. To see why that is true, just think about the fact that at the cutoff frequency, the magnitude of the transfer function should take on the value of 1 over root 2 instead of 1. So the value here should be 1 over root 2. It should never be 1. So the straight line approximation, after all, it's just an approximation. It's never like 100% accurate. It can never be 100% accurate. Just keep that in mind while you're drawing these straight line approximations in 16B.